Up to half the ordinary matter nearby is missing from our inventories. Short answer, it hides as hot, diffuse gas in cosmic filaments. Imagine a dim, vast web stretching between galaxy islands. The missing matter means ordinary atoms we cannot easily see. If we fail to count them, our cosmic bookkeeping breaks. Gravity pulled gas into long filaments. Shocks heated that gas to very high temperatures. That heat makes the gas faint in visible light, yet bright in UV and X-rays. So, most missing matter is ordinary gas spread hot and faint. A faint web of gas threads connects distant galaxies like bridges. This web contains the missing ordinary atoms, spread thin across space. You should care because that gas holds billions of suns worth of matter. Gravity pulled baryons into filaments after structure formed, and gas compressed along those filaments. Compression and shocks heated the material, so it rarely emits visible light. The gas mostly shines in ultraviolet or X-rays, which are hard to detect. For example, surveys at low redshift show nearly 50% of baryons unaccounted. So the cosmic web is the likely hiding place for ordinary atoms. First, dark matter and missing matter are different puzzles. Missing matter refers to baryons, ordinary atoms that normally emit or absorb light. This matters because baryons drive star formation and chemical enrichment. Early universe signals precisely predict baryon abundance from the cosmic microwave background. But local inventories of stars, cold gas, and hot halos add up to only about half that amount. That gap forces astronomers to search for baryons outside galaxies. So separating baryons from dark matter is essential for accurate cosmic budgets. Astronomers use bright background beacons to reveal faint intervening gas. When quasar light crosses gas, it leaves absorption fingerprints in the spectrum. Those fingerprints tell temperature, density, and chemical composition in one sightline. Instruments in the ultraviolet detect ions like oxygen and hydrogen at warm temperatures. X-ray telescopes target hotter plasma, where heavier ions emit. Researchers also use statistical stacking and scattering techniques to boost weak signals. For instance, a quasar absorption sightline can show a trace of oxygen that corresponds to many solar masses of baryons. So absorption and emission together let us count intergalactic gas. The warm-hot intergalactic medium fills the filaments between galaxies. It consists of highly ionized gas at temperatures from 10 to the 5 Kelvin to 10 to the 7 Kelvin. That heat keeps atoms stripped and radiation faint, so detection is challenging. Shocks from collapsing structures compress and heat the gas, changing ionization states. Simulations predict the WHIM contains between 30 and 60% of baryons today. Observations so far have recovered portions of that predicted mass already. Thus, the WHIM remains the prime suspect in the missing baryons case. Detecting faint WHIM gas demands ultrasensitive ultraviolet and X-ray instruments. Hubble's cosmic origin spectrograph proved crucial for ultraviolet absorption studies. X-ray observatories began to detect the hottest, rarest plasma in filaments. Recent stacked X-ray analyses reported filament emission around galaxy clusters. Future missions like Athena and Lynx promise much better spectral clarity. For example, stacked X-ray detections have already suggested millions of degrees gas between galaxy pairs. So instrument sensitivity strongly limits how much baryonic mass we can currently count. Researchers combine multiple weak signals to lift the WHIM out of noise. Stacking many galaxy pairs amplifies faint filament emission into a measurable result. The thermal Sunyaev-Zeldovich effect measures hot electron pressure by scattering microwave photons. Pairing TSZ with X-ray stacking yields mass and temperature estimates. Absorption line surveys add direct ion counts along individual sightlines. A 2019 study found TSZ between luminous galaxy pairs, implying large baryon masses. So combined techniques turn whispers of photons into a measurable baryon census. Despite progress, significant uncertainties still surround baryon counts. Different detection methods probe different temperature ranges and densities, creating mismatches. Instrument calibration, foreground subtraction, and stacking biases all complicate conclusions. Simulations help interpret observations, yet they depend on uncertain feedback physics from stars and black holes. Some claim detections proved weaker after reanalysis due to foregrounds or systematics. However, independent methods trending together increase confidence in the results. So the evidence points toward filaments, although exact baryon fractions remain debated. Where baryons reside shapes how galaxies form and evolve over time. Gas availability controls star formation rates and future galaxy growth. Some baryons cycle into galaxies, then get expelled by stellar and black hole feedback. Others remain in filaments and may be recreated slowly later. Quantifying these reservoirs tells us how efficient galaxy formation actually is. For example, if half the baryons sit outside galaxies, long-term star formation fueling becomes limited. So locating baryons clarifies the galaxy life cycle and cosmic chemical evolution. So most missing matter appears to be hot filament gas between galaxies. If you liked this clear take, subscribe for more space stories.